Peter Griffin. What in the hi? Oh, Maisha even beat. Oh my God. Excuse me. Very good. Okay, I'm 2 steps behind. Right, I have to let somebody in. But Peter Griffin. Oh my God. Do I? Whoa. Do I need? Oh, that's funny. I get that. Hold on. There's someone I got to let in. I think. Wait. Rodent. That's a mouse joke. I get it. Hold on. But why? Excuse me. Apparently, I need. Yes, there was a mouse. Oh my God, that mouse thing was crazy. Yes, there was a mouse in. Yes. Pay at a time. Yes, there's mice. There's Peter Griffin. There's May. Hi, May. I didn't even say hello to May. Hi. Hello, Eric. I didn't even say you could take care for a price. Excuse me. I don't know what my problem is. Sorry, it must be the most. Hi, good. Oh my God, dude. Hi, Newell. Hello, Jayla. I think Jayla, May, and Newell are getting A's because they don't ask for A's. They just work for their A's quietly and strongly. They just know, they have faith that if they do the right thing, the right grade will come to them. Anyway, and Elizabeth too. So there, and Lizzie. Not just everybody except for the people that I'm not. Yeah, that's how it is. No, it's totally not how it is. Well, it is how it is for them. I'm not saying, I didn't say it. All right, I'm gonna. Oh, more people coming. Oh, speaking of Lizzie, okay. How y'all doing, Peter Griffin? For heaven's sake. You would definitely love it. No, don't ask for it, Newell. You'll get it. You would love it. The A would love you, Newell. You're not. I literally. Okay, I'm gonna say this. My 7-year-old younger son that some of you have Zoom met. Oh, good save, Newell. Good. I mean, good. I like it, Newell. That's good. Wait. So yes, direct chat person. Peter Griffin is still in the 4th grade. Hi, Lizzie. Good to see you. Who's the Pokemon chick? Oh, yes, that one. Right. So that 7-year-old, so funny. This is related to the whole A thing and like what Noel just said. Right. That son, I mean, I do have 2, but yes, that son, he was playing with his cousin who's like 10. And I promised that I was going to buy the 10-year-old cousin a game, like Skyward Sword or something. I'd made the mistake of making this promise. And then the 10-year-old son like kept asking me every time he saw me, like, can you buy me Skyward Sword now? And yes, I am that kind of uncle who just like wants to buy people's love but anyway, so he's like okay, every time he sees me, Uncle Danny, are you gonna buy me Skyward Sword now? And I'm like, yeah, I gotta talk to your mom, whatever. And I walk out of the room and I overhear my 7-year-old son saying to the 10-year-old cousin, my troublemaking son, again, yes, some of you have met, and he ain't exactly no shrinking violet, like he's not exactly well behaved. I hear him saying to the 10-year-old, wait, are we recording this, by the way? Oh my God. I hear him saying to the 10-year-old, he goes, listen, Elijah, take it from me. I learned this the hard way when I first got my Nintendo Switch. The more you ask, the less likely you get it. When you stop asking, that's when you get what you want. I mean, I totally hear him saying this to his 10-year-old. Now, granted, that is a lesson that I certainly do try to teach, but I did not know that he had ever, there's no evidence whatsoever that my son had ever assimilated that lesson until, he thinks I'm not listening. And then there he is trying to instruct. You get my point. What is my point? Right. So, yeah, okay. So you get it. All right, thank you. I'll see. And Jayla, notice the subliminal cool thing that Jayla's doing. Jayla's just writing comments that have A's in them. She's right. She's not coming out and asking for an A. She's not doing anything to work it, but her comments have the letter A in it. So it subliminally gets into my mind and starts influencing me. I mean, that's how to play it. Right. All right. I'm totally kidding. Okay. Yeah. Capitalized. All right. Oh, wait. Yeah, no, and I agree, Eric. Oh, so now we know where Eric, cool. And Eric comes in with so he knows what's up with these games. Yeah, I agree. Skyward Sword's not that great of a game. It's okay. But right, okay. But they've already he's already won at Breath of the Wild and blah, blah, blah. But okay, tried to use Brian as a Pokemon, ended up getting arrested. That's hilarious. Okay. Okay. Shut up, Nick. Okay, that's funny, Peter Griffin. I get that. I do get that. Okay. So we have to do like some physics. We have to do some physics. It's good to see you all. I owe you a million things, maybe even A's. You owe me nothing. Let's just do some physics. My feet. So what are we doing? We're doing this. Oh, excuse me. Sorry. Okay. What we're gonna, whoa, I have a feeling that's directed at me. That's quite an emoji. Now I'm actually scared. Okay. No, okay. Oh, it was right, okay. But I kind of feel like I deserve that today. Okay. Physics. Okay, the top equation on the sheet right now is what we're all about right now. Like, what I want to make clear is the thing on the top of the page, d2x dt squared equals negative k over mx. That is a differential equation, one of many, our first. I mean, one of many in life, one of a few in this class. What it really is just Hooke's law written mathematically, right? We are encountering it because we're ultimately trying to figure out the physics implications of Hooke's law. We're ultimately trying to figure out for a system that goes back and forth under the influence of Hooke's law, for a system that we are now beginning to call a simple harmonic oscillator. We're trying to figure out how position depends on time, right? we are looking for x as a function of t for the simple harmonic oscillator. Concretely speaking, we're trying to solve question 9 of homework 1, right? This is all about question 9, but it really is actually a big question. So we're trying to get x as a function of t, but what we know so far is this differential equation at the top of the page. Okay, and I want to remind you, like, yet again, a differential equation, I mean, it is an equation for sure. It contains lots of information in it, but it is not, generally speaking, a differential equation really is a problem to be solved. It is not the answer to a question. It is not the solution to a problem. It is a problem that demands a solution. The solution that we're seeking is some kind of x as a function of t. We're looking for an x for which it is true that d2x over dt squared equals negative k over mx, okay? And once we get that x function of t, then first of all, we will have what we call a solution to this differential equation. Again, please hear me, because this is a kind of new thing for many of us. A differential equation is not an answer. It's not the thing you arrive at, it's the thing you start at. Well, an answer would be x as a function of t, okay? We're trying to find an x as a function of t for which it is the case that the time derivative of the time derivative of x is directly proportional to x itself. We're trying to find an x, which when you take the derivative with respect to time of the derivative with respect to time of that x, you get back x itself times some sort of constant, k over m is a constant, times a negative sign. That's what we're looking for. That's a little bit like almost backwards. It's almost like Jeopardy. Like we have the answer, we're looking for the question. I mean, it's a little bit of a new kind of backwards thinking. Now, we're looking for the answer. The truth is, I don't want to confuse anybody. The truth is, it's going to turn out, what it turns out to be the answer is written right here on the page as well, the second and third equations. But I want to be clear. That's what we're trying to figure out. Like, we haven't figured those out yet. That's where I'm going with this. Like, that's the conclusion, okay? What we have is the differential equation at the top. What I had said, okay, and sorry, hold on, let me look at the chat. Actually, a couple of things are happening in the chat. Oh, yeah. Wait, okay, actually, wait, no, this is a very important question. Maisha's question in the chat. Hang on, yes, it is the case. and I hope the reason she's asking, wait, let me stop for a second. Yes, this is an important logistical update. What I put in the Google Classroom, I hope you saw this week, Physics 204 lab is canceled for all sections. Like, I mean, including yours. Like you guys, wait, don't tell me if I'm, you guys normally have lab on Fridays, I believe, right? Right. Thank you, JLo. JLo's like just all over it today. And okay. Oh, okay. So thank you, Elizabeth. Thank you. And thank you for bringing this up, Maisha, but thank you, Jalen. Thank you for Elizabeth. Yes, yes, yes. So, okay. So you did see the thing. Yeah. There's no lab this Friday. If you just confirm that you received that thing in the Google Classroom, then you get 9 points. That is totally true. And if you already did it, you already get it, but you still can do it by then. But yeah, so I'm just making sure. So that's right. There's no lab this week for any Physics 204 class. So just make sure, Maisha, you're asking that because you're making sure, right? Like you did it, you saw it, but you're just like making sure. Yeah, yeah. Okay, good. No, thank you. That's right. That's right. And lab will resume next week for everybody. I'm just pausing whether to. Yeah, so that's the case. Okay. Yes. Did I say something wrong? And well, yes. The truth is, it is your section and it is all sections. So let me know. Did I write something in it, just in case anybody's not listening right now or someone's not in the Zoom right now? Did I write is there some way in which I wrote the announcement that made it confused? Like, did I accidentally say Thursday instead of Friday or something like that that made, okay, fair enough. And I totally appreciate that. So yes, there's no lab for you guys this week. And it will resume next week. Okay, cool, thank you. And also, please note that I did put in some of the new game participation portals, like, you know, when you're wrong, you get points. When you use video, you get points. So all of you right now, like Jayla, especially, who's totally like stepping up big time today, and Elizabeth with an S, and certainly Maisha, of course, did I say like? Please look at Peter Griffin, of course. I mean, I have to now enter a whole new name in the roster for him. But, oh, by the way, yes. I mean, I can't guarantee A's for anybody, but obviously Peter Griffin gets an A. I mean, I think that's fair. I mean, I think no one's, yeah, of course. And also Bart Simpson will get an A. I mean, like, of course. But please just note that there are more participation portals that have opened up, and definitely there's some people participating today a lot that don't you should take advantage. All these things count as participation. Okay. Okay. So now getting back to, Monday, we established that there's this differential equation that we're, oh wait, I'm sorry, May, that's a really good question. No, a very good question. I mean, they do, good question. So technically, any of those funky game portals, like submit for video or submit for if you use your voice during a Zoom class, or multiplayer co-op, like if you help out, if you mentioned something that someone else said, they're all due by the end of the semester. You could submit them anytime, and you could submit them more than once. If you use video a lot, you can submit video more than once. Or like in the example, for example, of May, I mean, not to call anybody, but May shows her picture a lot, like what I'm calling an avatar. It's not like it's really her picture. It's not an avatar, but like, and that's points. There's definitely one of the portals that's called avatar or something says that if you're showing anything other than a black box at all, which totally includes a picture of you, but also could include a picture of Peter Griffin, all joking aside, like you can submit that and you get points for that. And if you do it more than once, you could submit it more than once. Just to, oh, good. Okay, cool. Yeah, no, it's meant to be. Like literally, please, like some of the names are deceptive and some of the instructions are overly wordy, surprise. But please, any of you, when you get a moment or when you feel like it, just look through those game portals and see if anything applies to anything you ever do or have done. And whenever or if ever it applies, just submit. And it's not about submitting proof. It's about submitting a reminder to me and to you. And then you just get the points for it. And yes, so to answer May's question, they do have a due date on them. I think technically the due date is like May 15th or something, like it's like the last Friday in May. But basically what I meant by that is just whatever the last day of classes is in May. I just didn't know offhand. So you could do them anytime. And also you don't have to do them, but it's just for points. Okay. And more like that will open up too, as long as we're talking about this right now. And this may in fact come up today. Oh, wait. Lois can be overly worried. I'm definitely overly worried. Now let me give you a funny example now too, since May is asking this question, and it's a good question. Freaking sweet. Okay, that is totally, I shouldn't even get this reference, but I do because I have two sons who watch these kind of, all right. But on May's question, let me say to everybody again, and especially people who haven't had me before, like notice, okay, and I'm not calling her out. I mean, I am, but like as praise, not as embarrassment. So May asked this question, right? She asked it in the chat. Already that's some kind of points that she could submit to. But then I answered it. Well, I want to say right now, if at any moment, May puts into the chat now, like, got it, thanks, or sweet, or I understand, or like Elizabeth wrote, that's cool. I don't know if she meant it to Peter Griffin or to me, but okay. So now what May, thank you. She's totally paying attention. So what May just did, and it's not only May, and this is not a competition, right? Anybody can do these things and get these points, but just to make it clear, right? Oh, I never noticed that. That's funny. But to make it clear, like May asked a question, I answered it, and then she bookended the whole thing. She like acknowledged that I answered her question. She gave me permission to go on and assume that she was clear now. She said thanks or whatever. I call that or closing a conversational path. Like there's a portal for even just doing that. You might think I'm silly or whatever, but I think it's like really important and helpful, especially in Zoom learning and all that. If you can, if a person can show the other person that their answer landed, like it's all good now, thank you, then that other person can go on with their lives. And you all know me, if I'm not sure if I've answered something clearly, I'm going to just keep going on and on and on, like still trying to answer it. So it's like a favor to the whole class that May is like, yeah, got it. Good. Thank you. So she can submit that for points. It's called closing a conversational path. And it's not just her. It also applies to Maisha and I'm not, but just to be clear. So look through those portals, any kind of way that we're like aiding the whole class dynamic. And also, of course, showing that we're paying attention. Like that's good. Okay. So, okay. 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 Can I join your group? Yeah. Okay. Sorry. But also notice that there's at least one portal for if you ever have and this is going to be, I'm about to actually ask you to do something mathematical, like all of you. And I did in the other section this morning, and actually a lot of them had a lot of questions, and it actually turned into sort of challenging for some people. And I did get to find out like how comfortable people are with calculus or what. I want to encourage you right now. I'm about to give you a thing to do in calculus, in this class, and all kinds of things you could put in the chat to let me know where your thinking is. All different kinds of things are very helpful. For example, if you write something in the chat that turns out to be wrong, there's a portal for that. There's a portal called Be Wrong, Be Really, Really Wrong. If I literally tell you that something, even if I say it politely, like, okay, you're not quite there yet, don't forget the chain rule or something, then I want you to submit that for points, because I want to encourage and the guts and the guts that it takes to say something that might then be wrong. And I want to reinforce the idea that we have to be comfortable being wrong in science, like a lot. So anyway, okay, enough about that. So what are we going to do now? This guy, that's funny. Okay, I don't know which guy you mean, by the way, but okay. So here's the thing that we're going to do now, or whatever. Like we're trying to find a function, x of a function of t. We don't know what it is. We know it has to meet a requirement called the differential equation. We know we're looking for an x that has to do something once we take its second derivative. So what I mentioned on Monday is what we actually do is we conjecture and verify. We guess and check. We try something based on our experience or our lab experience or our visualization of what might happen in the lab. We try some kind of function. We consider the details of that function. We try it. And then if it's right, we win, we're done. If it's wrong, we don't throw it away and go home and just cry. we see what's wrong with it and we try to tweak that and we try again. So it's a little bit like trial and error. In other words, this is a very sort of scientific experimental way to solve a math problem. And let me tell you that some math problems, in fact, most real ones, really do have to be solved this way. Most of the math we learn in math classes about how just to like take out the tool and do the procedure and get the thing right. That's what people figured out after the fact. That's not how, when they're originally solving things, they have to play around and take risks and try things and see if they work. The way mathematicians and physicists solve certain differential equations is they try things and then see if they work or not. That's what we're going to do here. So first of all, so what we mentioned last class is we're going to try some kind of cosine function. The reason we're trying a cosine function is we're picturing a mass going back and forth on a spring. We're asking for any given time, where is the mass, right? So we were thinking to ourselves, if we were to plot time on the x-axis and plot position on the y-axis, maybe that's a little confusing to some of us, but if we're plotting time, in other words, on the independent variable axis, and we're plotting position x on the dependent variable axis, then we would have an x value that would be going back and forth and back and forth and back and forth as time elapsed, perhaps like a cosine graph. So we're going to try some cosine function. Last Monday, or 2 days ago, the way I wrote it was like x equals blank cosine blank t. I put blanks in because I said, okay, we're trying some sort of cosine function. But before we even try it, we have to be, we can do better than that. Before we actually try it, we have to be a little bit more specific and a little bit more detailed. We have to realize as physicists, as scientists, that all these values, t and x, these variables are actual measurements that we make in the lab. T stands for time, measured in seconds. X stands for position, measured in meters. Hang on a second. Yeah. Hold on one second. Yes, no, thank you. That's great. Direct chat person. So someone in the direct chat is asking me to repeat something I just said. It was important, so I'm glad to repeat it. And direct chat person, you can submit that for points, please do. Like, I'm glad to do this. Okay, so what I just said a second ago, in fact, this is in your notes. This is in your notes, but for Monday, Peter, okay, hold on a second. What I'm saying is this: if you picture yourself being in the lab and you picture a mass going back and forth on a spring, like, which is our situation here, a mass is going back and forth on a spring, and you picture yourself every second asking where is the mass? Like, you picture yourself making time measurements, like, okay, every second I'm going to make a measurement with a ruler and see where is the mass, like at how many meters or millimeters or centimeters is it away from equilibrium. So like at time equals 1, you find that the mass is over here. Then at time equals 2 seconds, you find that the mass is over here. Then at time equals 3 seconds, you find that the mass is over here. And if you kept doing that for a long time, as the mass went back and forth and back and forth and back and forth, and you made a whole table of values, t and x, right? If you then put those values on a graph, so this is the part that someone is asking me to repeat. I'm saying if you took a whole bunch of measurements, t measurements as your independent variable and x measurements as your dependent variable, and then you got all these values and you put them into a scatter plot, made a graph out of it. And if for that graph, time was your independent variable, in other words, your horizontal axis, and if x were your dependent variable, in other words, your vertical axis, I think what you would find, and I think you would think this too, if you think about it, you would find that the dots on your scatter plot would go like they would start at somewhere, then the positions would start heading towards the equilibrium position, then they would pass the equilibrium position and keep going down past it as time elapsed, and then they would come back up toward the equilibrium position and then go past it all the way to the other side, and then go, In other words, I think your graph would look like this. It would be like a cosine graph, I think is what I'm saying. And I think we said this on Monday, like, right? Because it would be some sort of smooth up and down thing that keeps crossing the x-axis to above it and then crosses the x-axis to below it and then but it would be doing that over time. So in other words, your mass is going back and forth, back and forth, back and forth in a straight line. But if you graph that where time is on this axis and position is on this axis, then the graph would go up and down, up and down, up and down in time. And it would look like peak, valley, peak, valley, peak, valley, I think. And maybe the direct chat person who asked me that could tell me in the direct chat whether I'm answering or not, because this is definitely an important point. I think the graph of x as a function of t would look essentially, okay, cool, thank you. Okay, cool. And that's definitely points and blah, blah, blah. Would look, so what I'm saying to everybody is, I think the graph of your xt scatter plot data, I'm conjecturing, I believe it would look like a cosine graph. By the way, right, because it would go up and down, up and down, up and down, or so to speak, back and forth, back and forth. Some of you might be wondering, why do I keep saying cosine? Why don't I say sine? Fair question. You could say sine as well, but the reason I'm saying cosine is because remember, the sine graph starts at 0, 0. The sine of 0 is 0, right? And our mass did not start at 0. And like at time equals 0, the mass was not at 0. And it couldn't have been, because if it were, it would never go anywhere. If we just started at equilibrium position, it wouldn't go anywhere. We started it at some positive value that for us happened to be positive 15 centimeters, right? It didn't matter that it happens to be 15. It could have been 13 centimeters. It could have been 27 centimeters, whatever that number of centimeters, or it could have been meters, whatever it was. We actually called that the initial value of x. We called it x naught. And x naught was not 0. It was definitely something else. So the mass started up here, like on a graph, it started up here and started heading toward the x-axis. And then it passed the x-axis, which is equilibrium, and then got to the other side and then came back, right? So it was doing this, but in time. So it was doing that. So I think it's a cosine graph. I'm guessing it's going to be a cosine graph. So I might guess, okay, x equals cosine t. But what I said Monday was that's not good enough. Like, that's a good start. I think x is some kind of function of cosine t. But I can't literally just say x equals cosine of t because I'm a scientist. These are measurements. Measurements take units. And I don't think you can take the cosine of a second. Oh, excuse me for 1 second. I'm sorry. Hold on 1 second. So I don't think you can take the cosine of a second. Furthermore, when you take the cosine of a number, what you get back is, I don't think you can take the cosine of a second. You have to take the cosine of like an angle or something measured in radians, maybe degrees if you want to be like primitive about it. But at this level of sophistication, we would take the cosine of something measured in radians. And when we get the cosine, the output of cosine is a pure number, like the cosine of say 60 degrees, or in other words, the cosine of 60 degrees, or in other words, of pi over 3 radians, is 1/2. It's not 1/2 meters or 1/2 kilograms or anything like that. So what I'm saying is, if you look at this top line right here, that's funny. Okay. If you look at this top equation here, this is my conjecture. Let's be very clear and careful about this. This is my guess. I haven't proved that it's right. I'm building a guess. I'm building a conjecture. The cosine I guessed because of what I'm saying about what the lab data would look like. Then I'm guessing that there has to be some sort of constant written before the t some kind of constant whose units are radians per second. Like again, note I always use square brackets as meaning units, right? So notice, I put this letter next to the T. The letter that I put next to the T happens to, it looks like a W. It happens to be a lowercase omega. I mean, the Greek letter omega, lowercase. I'm just choosing a letter. I could have, okay, wait, hold on one second through the joke. Sorry, let me just get this. I'm choosing a letter. I could have chosen any letter, B, C for constant, but I happen to be just choosing a Greek letter. Don't let that intimidate you. It's just an arbitrary letter. And it just happens to be the one that all other physicists choose. So I'm just trying to communicate with other physicists. But I put a letter before the T. All I know about it is that it's some value, some constant value that must be measured in radians per second. Then the seconds will cancel out, like radians per second, so that I cancel out the seconds in time in the T value, and I'm left with radians, right? I just know that there's got to be something there to make those units work. So then I take the cosine of something measured in radians. Then it's going to spit out some number. It's going to spit out some number between 1 and -1, some literal dimensionless pure number between 1 and -1. Well, my final answer for X is not supposed to be just a pure number between 1 and -1. It's supposed to be some sort of displacement, some sort of position measured in meters. So I say there's got to be a letter, a constant, that multiplies the cosine, and that constant's got to be measured in meters, so that my final answer at the end of the day is actually measured in meters. Now, for that constant too, I could have just made up another name. I could have made up some other Greek letter or something. But then I realized, wait a second, I actually know something about what that number needs to be. Like if I really think about it, like if you turn your head and look in the red on the side of the page, it's reminding you like the sine of 0 is 0. Sine of 0 is 0. Cosine of 0 is 1, right? In fact, again, that's like why we've chosen the cosine function here. It's not very easy to read, but it says cosine of 0 is 1. Hold, bear with me, just make that easier to read. The cosine of 0 is 1. What's my point? My point is, if you think about it, when time equals 0, if you in your head plug in 0 for T, then you multiply that by omega, whatever omega is, I don't care. If you multiply it by 0, you get 0. So then it says take the cosine of 0. Cosine of 0 will be 1. So that means the highest value we're ever going to get for that cosine term is 1. Well, it's like saying that would, if the cosine were left alone and we're not multiplied by something before it, that would be saying that our mass is oscillating back and forth between position +1 and position -1, position +1 and position -1. But we know this is all about question 9. We're still all on question 9 here. Okay. So I'm saying we know where the mass was when T equals 0. When T equals 0, the mass was at positive 0.15 meters from equilibrium in the context of this homework, in homework sheet 1. When T equals 0, X was its initial value, happens to be 0.15 meters in this case. In general, we call that initial value X naught. So I'm saying, think about X naught is like a scaling factor on the range of cosine. Cosine ranges from -1 to +1. We actually want the position of this mass. Let me say that again. Cosine ranges from the number, the pure number -1 to the pure number +1. We want our X values to range from negative X naught meters, like negative 0.15 meters, to positive 0.15 meters. So if we multiply the whole cosine expression by X naught, that will mean whatever cosine spits out, we multiply by X naught. And in the extreme example where T equals 0, then X will be equal to X naught, which by definition must be the case. So what am I saying with all of this? I'm saying that right now I have a guess in mind, a conjecture, a guess that I'm arguing where I came up. I have a guess that X is this function, X naught cosine omega t. I have not proved that it's right yet. I'm trying to argue why I'm even using it as my guess. I'm trying to argue where I even came up with this idea in the first place. And I came up with it thinking about what's happening in the lab, or what would happen in the lab with a mass going back and forth and making measurements. So I'm guessing, remember again, folks, we're looking, and remember I warned everybody too, Physics 204 is a little bit more mathy than Physics 203. And the math of Physics 204 is true math. It's not a bunch of numbers. It's a bunch of equations. Really, it's a bunch of functions. That's what we're looking at here. We're trying to derive general relationships between one measured variable or one variable measurement and another. So the function that I'm guessing here, would describe the equation of motion, the behavior of a mass going back and forth on a spring. I'm guessing that it's X equals X naught, where X naught is the initial value measured in meters, times cosine of omega times t. What is omega? And honestly, if you're still with me at all, what I would think if I were in your position or having been in your position before, if you're still with me, I would maybe think that the part that might be the most confusing right now, or the one thing that might be annoying to many of you, is I'm sort of getting what he's saying, but what's the deal with omega again? Where the heck did omega come from? What I'm telling you all is, I've never mentioned omega before. This is my introduction of omega. In fact, it says here in the notes, it says it says we hereby introduce, I'm saying there's got to be some number measured in radians per second, multiplying that t. From here on in, I introduce the letter omega. Omega is the name I'm going to give to whatever that constant number is, measured in radians per second. I don't know anything about omega other than it's got to be some constant number that's measured in radians per second. But with that, I'm guessing that my function is X equals X naught cos omega t. Now, that's my guess. How can I prove that it's right? Or why should I believe it? Remember, here the answer is we take derivatives. We're going to test this guess by taking derivatives, a certain number of derivatives. I'll tell you how many. We're going to take 2 derivatives. Why are we going to take 2 derivatives? Because this is supposed to be an answer to, it's supposed to be a solution to this differential equation on the top of the page. We're trying to figure out an X such that when you take the time derivative of X and then you take the time derivative of that, like when you take the derivative of X, in other words, when you take but the whole goal of this is to make you not understand, so just bear with me. But I understand, but yes, this is calculus-ish, yes. But I'm trying to teach it. I'm not trying to assume that you know it, but we are about to practice it right now for real. I'm saying we're looking for an X such that the derivative of X equals X itself times some bunch of constants times a negative sign. That's what we're looking for. And that's a weird thing. I'm not saying it's easy, but I'm trying to explain it. I'm saying we're looking for an X function for which it is the case that when you take 2 derivatives of that X function, you get back that X function times a constant times a negative sign. So we're guessing this cosine function. How can we know if we're right or wrong? The way to know is to take a derivative of it and then take a derivative again and see what happens. So that's what we're about to do. And I'm not saying this is easy, but I am saying it's super doable. I'm not saying that I think all of you walked into this class knowing how to do this. I am saying you're going to be able to walk out of this. Oh, cool. Oh, wow. I got to open up a portal for that. Talk about closing a conversation. You just took me on an emotional roller coaster ride that ended in a really good place. Thank you, Jayla. Okay, so So good. So what we're all going to do, we are going to take, I'm going to shut up with C44. Yeah. Now, some of you are going to really appreciate this and some of you are not. But literally what I'm going to ask you all to do now, I'm going to ask you to not use the public chat. I'm going to ask you, this is a do now, like this is a you, please do this, you as individuals. I'm going to ask you to take the derivative of the given function and then take the second derivative of that and then stop. Like the function is x equals x naught cosine omega t. That's the function. Notice t is the independent variable, x is the dependent variable. Like so x and t are acting here like if this were a math class, x and t are acting like y and x. In fact, if you're really having problems with this, you might even change, you could change the x to a y if that makes it easier for you. And you could change the t to an x if that makes it easier for you to picture. But then notice that the x naught and the omega are just like numbers. They're just constants. You could change those to like a 5 and a 3 if you want. Well, okay, wait, hold on. Well, good start, but hang on. I'm saying now you're going to take this function x equals x naught cosine omega t, and you're going to take the derivative of it. You're going to get dx dt. Then you're going to take the derivative of that, get t2x dt squared. And one person I appreciate. What I want is you to give me, all of you, any of you, and this counts for points and all that. Give me your thoughts in the direct chat. Like either give me an answer if you think you can get an answer, or give me a question. But let's do this in direct chat so that it's not a race. It is not a competition. Like everybody can get this right. But but this is for you. Okay, wait. Okay. And also, sorry, I don't mean to be, can we slow down the jokes for just right now? Because this is hard enough and kind of intense enough that let's just stay focused on this for right now, for everybody's sake, not to be rude. I mean, I do love the jokes. Yeah, I do generally, but I'm getting myself confused. I'm not totally sure what's a joke and what's not. So just for the moment, because I know some people find this very intimidating. Okay. All right. Then I apologize. So here's the thing to everybody. Okay. So that wasn't a joke. Here's the thing though. If you follow what I'm saying, or if you try to follow what I'm saying, there's not going to be any number. I'm not asking yet for the answer to question 9. If you do what I'm asking you guys to do right now, like all of you, there's not going to be numbers in your answer. I'm asking you to do pretend it's a calculus class. Forgive me. Take this function, x equals x naught cosine omega t, and get dx dt of it. It's like me saying, here's a function, y equals a cosine b x, and then I'm asking what's dy dx of that. Like that, I want the first derivative of it. So your answer is going to be a function. It's not going to, I mean, it might have sort of numbers in it, but it's not going to be a number. And then you're going to take the derivative of that again, and you're going to get another function. You're going to get functions. And I'll give you a hint, all of you, your answers are going to have like sines or cosines or something in them. And then you're just going to leave them like that. But so I'm going to start looking at the chat now, but your task is you take this function, this is your function, x. Well, here, I'll write it, like in other words, and this is important. Like, and it might, some of you will find this very easy, some of you will find it hard, but my goal is that all of you will find it clear once we're done. Hold on, just. Okay, let me look at this. Okay, so I'm looking at the chat now. Oh, and I'll tell everybody, if this goes sort of the way I want it to and the way it did in the other class, you're going to be working on this, all of you, and you're putting things in the direct chat. And I'm going to just be quietly responding to direct chat right now. So forgive me. Like it's more like a bunch of one-on-one conversations right now rather than a group. So you'll have to be patient with me. If you think this is totally easy and you think you've just nailed it and you think you have answers, then I'd recommend going back to the first page of notes and seeing if your answer, if you can make sense out of what I'm saying on the first page of notes, like see if, but just bear with me. I'm going to sit here and respond, but I want everybody to try this. This is important. And if you're stuck, then tell me how or where you're stuck. Like, don't just give up on this. Okay. Oh, I'm sorry. Someone asked, does the message have to be private? The message doesn't have to be, but it might be useful right now to keep them private just because I don't want anybody to like feel rushed by anybody else or feel like they can't try this just because someone else did. So let's try to keep them private now, but it's not a big deal. So let me, hold on. some of the, and I apologize. I know this is, some of the things that are happening in the chat are very good. Wait. Oh, great question. Sorry. And we will reunite shortly, but I'm really, okay, I think, okay. This is, okay, I'm gonna start talking in a second. I think you guys are actually doing very good things in the chat. We have, yeah, okay. So let me say a couple of things. And this is, and I mean this totally seriously. A lot of really good things happen in the chat. To be totally honest, this is one of the things that I know we all would prefer not to be Zoom learning, but this whole private chat thing is the one aspect of all this where I feel like things are happening in the private chat with you guys that actually can't happen any other way. I think many of you, oh, okay. Sorry, I'm about to be slightly interrupted by my, but I think many of you are like honestly showing me your work and your thoughts in a way that you might not be comfortable showing everybody else, or that we don't usually have an opportunity to do in the middle of class. And I really appreciate it. Like, and the reason I'm saying this like so cheesily, and by the way, I'm going to say we we have 13 minutes left. We're about to be interrupted for a minute. So I'm going to ask, because I do want to give you the answers to this. I do want to show you this. And I think everybody was struggling a little bit in the chat. Like almost nobody like literally exactly has the answers. And that's not a criticism. That is, okay, we need to like, this is worthwhile time for us to figure this out. And if it took us all semester, I would think it'd be worth it. Okay, we're going to figure this out and we need this. I think all of you can benefit from this discussion, but I really want you to know that my ability to teach you this is much, much higher as a result of how honest and clear you're being in the chat with me. Again, let me just reinforce, I don't care where you are in calculus, as long as you honestly show me where you are and you're open to the possibility that we can take you higher. Okay, and that's what we're about to do. Because yes, I think there's some struggles here. Let me also lastly reinforce anything you put in the chat now, especially if you said something wrong or you said something right, or then I corrected you and then you got back to me. Please submit it all in the portals for points. Like you do deserve that. But okay, now what I'm going to say. So I'm going to say I'm going to try to explain this for the next 12 minutes. First, we're going to get interrupted for a second. My son walking in from school. Then I'm going to feel a little pressed for time. So I'm just going to ask you in advance, let's just try to be, hello. Let's just try to be actually serious for the next 11 minutes, like no jokes or anything. I mean, I often encourage them. I do encourage them. But for the next 11 minutes, let's try to just be focused on this so we can get it before the class ends. Okay. And that's, again, knowing that there is going to be a quick interruption, for which I apologize. Or maybe there won't be, but okay. So I'm going to turn to the next page. Hi. Okay. And yes. And I'm going to start by saying this is a complicated function that we're trying to differentiate here. It's complicated, it has a lot of letters in it, and it's x as a function of t. What you're used to seeing in math class is y as a function of x. So that's part of what's throwing some of you off. And you're used to seeing some numbers often, whereas I have a lot of letters. So I'm going to try to break this thing down. And please, thank you. I'm going to try to break this thing down, and I'm going to try to break this thing down. And wait, do you want me to take off your shoes? Well, here, I'll go to the. Okay, here's the next one. Okay, so if you look at the next page, I'm saying what you have is x equals x naught cosine omega t. That's a little bit. Okay. That's a little bit intimidating. But imagine for a moment that you instead, they were a math class, and you had instead y equals 5 cosine of 3x. Okay, and I asked you what's dy dx. In fact, I'm going to take it a step further. Tell me if you need time to copy. In fact, even before you copy that, take it a step further. Just first of all, imagine that in a math class, I wrote y equals cosine of x. Then what I think, based on the chat, what I think a lot of you are comfortable with, or maybe you remember even if you didn't initially, is if I said that y equals cosine of x, you would say dy dx equals negative sine of x, right? Like the derivative of cosine is negative sine. Okay, so here we don't have y and x, we have x and t. So I'm just like, I'm trying to explain what's on the page here. So if here I said x equals cosine of t, what's dx dt? You would tell me negative sine t. And honestly, again, like a lot of people either right away or eventually said something like this in the chat. So we're good so far. So that's one piece of what we're doing, that the derivative of the general cosine function is a negative sine function. Now, take it one step more complicated. Imagine that I put a number before the cosine x, right? Like imagine I had like y equals 5 cosine x. I think, if you think of it this way, I think that's like if I said y equals 5ax squared, what's the derivative? If I said y equals 5ax squared, what's dy dx? Or even better, sorry, let's say if I had y equals 5, if I had y equals 5x, what's the derivative? Most of you know it's 5. Dy dx would be 5, right? And here, I'm not saying this right, but here, if we have y equals 5 times cosine of x, you just hold that y is just a constant multiplier on the rest of the function. It just stays there and gets carried along for the ride. So you would say dy dx equals -5 sine of x, right? I think most, and again, I know I'm talking a little fast now, and I'm going to talk even faster. If you're uncomfortable with that I just said, make a note of it, and you can tell me this later. There's no shame at all if you're uncomfortable with that little step that I just did. You might be making a good judgment by not wanting to mention it to the whole class right now, but feel free to tell me later if you need a little help with that, okay? There's no shame in it, but I am saying for the moment, I think if we had y equals 5 cosine of x, the derivative dy dx would be -5 sine x, okay? Now I'm going to take it one step further. Say that 5 wasn't a 5. Say it was just a letter, like the letter M, right? And say the x wasn't an x, it was a t. Like, let's say we had x equals m cosine of t. If I asked you what's dx dt, you would say it's -m sine of t, I think, right? I'm just trying to show you piece by piece what we, right? So we didn't have m, we had x naught. Okay, same thing. In fact, it is the same thing. X naught is just a constant, just like m. But frankly, for many of us, that might be confusing. You might not realize that because x naught looks like it's a variable. I mean, it looks like some version of x or something. It looks that way. But the truth is, yes, x is a variable, but x naught is not. X naught is just the initial value of x. It is literally even though the value of x changes all the time, whatever its first value was doesn't change all the time. Like in our case, in homework 1, the initial value of x was 0.15 meters. That's always going to be the initial value of x. So x naught is a constant. It's not a variable. Hence, we treat it just like the m. If we had x equals x naught cosine of omega t, then dx dt would be -x naught sine of t. So we're almost, technically, I brought the negative sign out, as you see in that penultimate line. So we're almost there. We've done almost all of the heavy lifting. And if you think the answer to the first derivative was, in fact, -x naught sine of t, you're darn close. And I probably wrote in the chat, like, you're almost perfect. But there's one more issue, which is that RT is multiplied by omega, right? The actual function we're dealing with here is x equals x naught cosine of omega t. So how do we deal with that? Like that omega there is not, it is a constant. It is a constant, just like x naught, but it's not multiplying the entire expression. It's in the parentheses, just multiplying the independent variable. So what's up with that? If you really think about it, what we have here is a function of a function, right? What we're saying is take t as your independent variable, treat it like your input, plug it into the box, the first function box that multiplies it by omega. So first we multiply t by omega, then that box spits out an output called omega t. Then we stick that into a new box, a second box, a final outer function, which tells us to take the cosine of it, right? So we're taking we're applying a function to a function. We're taking the cosine of t multiplied by omega. What do we do in calculus? And I know we have 4 minutes. What do we do in calculus when we have a function of a function? We do something called the chain rule. That might be a horrible memory for some of you. It might be an awful deja vu. But here's my way of understanding the chain rule. The chain rule says, if y equals some function of x, I'm just reading off the sheet here. If y equals some function of x, and then you have some other function z of y. So if y is like an inner function of x input, y output, and then if y itself becomes the input into some other box that spits out z, then the derivative of the whole thing, the derivative of the outer, the derivative of dz with respect to the ultimate independent variable x, dz dx is equal to dz dy times dy dx. If you look at that last line on the page, it almost makes the chain rule look like it makes sense. I mean, it certainly does to me when I write it like that. It's just saying the whole derivative is the derivative of the outer times the derivative of the inner. So what does that mean to us? And I know I'm talking fast, I'm watching the clock. What that means to us is like our inner function here, like we can call it z, is omega t. The inner function is omega times z. What's the derivative of that? It's just omega, right? Like what's if y equals mx plus b, what's dy dx? It's m, right? I know, again, I'm talking fast and I will slow this down on Monday, or you should watch a video again and let it sink in and think about it, or ask me questions. But I think this, well, I'm trying to tell you, and I'll talk slower if you want Monday, but I am trying to say, don't give up on this. It actually does make sense, and it can make sense to all of you, even if it was 3 years ago that you took calculus or whatever. I'm saying though, that the derivative of that inner part is just omega, right? The derivative of the inner part is omega. Therefore, if the whole function is x equals, and we're just about done, if the whole function is x equals x naught times cosine omega t, that means we take the derivative of the whole outer and then multiply by the derivative of the inner. We're going to say that the final derivative is negative x naught sine omega t, all of it times omega. So then I just collect all the constant terms to clean it up. I bring the omega to the outside, and I get that the derivative is dx dt equals negative x naught omega times sine of omega t. And bear with me again, and I know we have like 1 minute, and if you have to go, then go. I'm going to go over like a minute and a half. I apologize if you have to go, but I just want to, and obviously I'm going to post these notes, but please forgive me and bear with me for like an extra minute and a half, just so we can get, and if you have to go, go, but if you don't have to go, just bear with me so we can get to the punchline of this, which we almost are. I'm saying the derivative is dx dt is negative x naught omega times sine of omega t. Most of you, a lot of you, by the time you were working this through, had most of that answer. You just didn't know that the omega was there sitting at the front as well. I'm saying it is because of chain rule. I'm saying the omega came out and got multiplied by the whole thing because of chain rule. Then I'm doing one more thing on the next page. This is my last minute. I'm saying that's dx dt though. That's the answer to dx dt. We'll pick up from almost that on Monday, but then I asked you to take the derivative again. So if you take the derivative again, you can practice on your own, but the derivative of sine is cosine, right? So the sine changes to a cosine again. The negative signs don't change anymore because like the derivative of cosine is negative sine, but the derivative of sine is just cosine. So we don't do any more negativing. The negative sign just stays along for the ride, but we have chain rule again. So the omega comes out again. So the second derivative, d2x dt squared equals negative x naught omega squared. Why squared? Because omega came out again from chain rule again, because omega has been sitting there the whole time in the parentheses. We get negative x naught omega squared cosine omega t. That looks like a big bunch of garbage. Like, so what? Why was this worth our life? Because notice this, if I just, multiplication's commutative, if I just rearrange the terms a little bit, if I just shove that x naught inside, then I have that d2x equals negative omega squared times x naught cos omega t. What is x naught cos omega t? It was our original conjecture for x. We were conjecturing that x equals x naught times cosine omega t. So it seems like what I'm saying here, you might want to let this sink in. You might have to think about it. We will say it again Monday. But apparently, if we guessed that x equals x naught, oh, cool. Very cool. I see that. Direct person. We conjectured that the right function is x equals x naught times cosine omega t. And then we tested it. We took a derivative and we took a derivative again. And what do we find when we take that second derivative? Oh my gosh, what do we get? We get back x, the original x, times some kind of constant times a negative sign. That's exactly what we wanted. The original differential equation said we're looking for an x such that when we take two derivatives of it with respect to time, we get back itself times a constant times a negative sign. That's what we got. So apparently this is x, as long as this omega squared thing that's just sitting there is just another name for the original constant k over m. As long as omega squared and k over m mean the same thing, then indeed x is x naught cosine omega t. That we will slow that down and talk about it more on Monday. But I would encourage you to rewatch the video or whatever. But that's it. Have a great day. Yes, have a great day. But by the way, to John Ford and to Peter Gray and everything else, that is, if you plug in 1 for t into that expression, then you'll get the answer to question 9, which is 0.116 meters, I believe. Okay, it's very funny. Okay, all right. That was it. Thank you guys for indulging me the extra 3 minutes. That technically is the answer to question 9. But anyway, we'll revisit that Monday. But thank you. Have a great weekend, all of you. You are the best. And have a great night. Yes, have a great night. And thank you, guys. Really great job. Seriously, seriously. Oh, cool. Great. And oh, I like what I see in the chat at the end here. Great. Thank you, guys. Seriously, thank you. Okay, cool, cool.